Hello students, how are you? I hope everybody are okay. This is a very tough situation all of us, and we hope we recover it soon. Please stay in home, stay safe. Okay, so today we studied a new topic of this chapter, that is electric potential energy. We know that the potential means energy possessed by a system of charges or energy possessed by a body by virtue of its position. That means when an object is at rest, due to that position, whatever the energy possessed, that is called potential energy. And when the object is in motion, that type of energy is called kinetic energy. Now in this chapter, electric potential energy, that means this type of energy possessed by electric charges. And we know that electrostatic force is a conservative force. So whatever the work is done by the charges against the force, that work done is stored as a potential energy inside the charge bodies. So whenever we derive or solve any numerical or anything related to potential energy, first of all we find out the work done. If we find out the work done, and that value is the potential energy, because work done is stored as a potential energy inside the charge body. Okay, so how we define electric potential energy? The electric potential energy of a system of point charges may be defined as the amount of work done in assembling the charges at their locations by bringing them from infinity. So whatever the work has to be done to bring that point charges from infinity to their location, that work done is stored as a potential energy inside the charge bodies. And this potential energy is measured in the unit, that is joule, and it is denoted by capital U. Clear? Okay. So now we derive the expression for potential energy. How we derive this one? This is a diagram. What is a diagram? First of all, you consider only at point A, Q charge is there. No other charge is there. Okay. Q charge is at rest at point O. So when the Q charge is there, that means no work has to be done, because before placing the charge Q, there is no charge is there, no field is there. So no force is experienced by this charge Q, and so the so no work has to be done by this charge Q. So we can say that because no work has to be done, so then because there is no electric field, that means W1 equals to 0. W1 is a work done due to first charge, that's why we denoted by W1. Now when we place the Q charge, it creates an electric field, and we consider another one point B at a distance R from it. So at point B, what is the potential? And we know that the potential is V equals to 1 by 4 pi epsilon naught Q by R. So first we consider at point A the Q is at rest. Now we consider at point B the potential due to this charge Q, that is V1 equals to 1 by 4 pi epsilon naught Q by R. Now we bring another charge Q0 from infinity to the point B. So when we bring this charge, second charge, that is Q naught or Q0 at point B, it experiences a force because this charge is placed here and it has an electric field, so it apply one force on this second charge. Okay, and so against this electrostatic force, this second charge Q naught, the work has to be done by the second charge Q naught. So, and that work done W2 equals to V1 into Q naught. We know that from the definition of electric potential, V equals to W by Q. So W2 equals to, because of the second charge, work done has to be done by the second charge. That's why W2 equals to V1 into Q naught. Now we put the value of V1 here. So we have W2 equals to Q naught by 4 pi epsilon naught R. Okay. So as we know that the work done is stored as the potential energy. So this is a system of two charges. Now at point A Q charge is there, at point B Q naught charge is there. So this behaves as a system, and this system is consisting of two charges. So the total work done of this system, that is W equals to W1 plus W2, and as we know that work done is stored as a potential energy, so we can write U equals to, or you can also write W equals to U equals to W1 plus W2. W1 is 0, so only W2 is there. So what is the expression of potential energy of this system? 1 by 4 pi epsilon naught Q naught by R. In place of Q naught, you also consider Q1 and Q2. No problem is there. Complete? Understand? So potential energy is the energy possessed by a system of charges by virtue of their position. We know that electrostatic force is a conservative force, so work done by the charges against the force stored as a potential energy inside the charge bodies. It is measured in joules. It is denoted by U, and the potential energy of a two-body system is U equals to 1 by 4 pi epsilon naught Q naught by R. This is it for two-body charges, two system of two charges. Now if three charges is there, then what happens? So this is a potential energy of a system of 3-point charges. So 3-point charges Q1, Q2, another one is Q3. So at point A, first we consider only at point A Q1 is there. So when Q1 is at rest, no work has to be done by this charge. So W1 equals to 0. Now at point B, now if we consider at point B, so it has a potential, and if we bring another charge Q2 from infinity to that point B, so work has to be done by this second charge, and that is equals to 1 by 4 pi epsilon naught Q1 Q2 by R12, or we can say that this is a potential of at point B. Now at point C, when we bring the charge Q3 from infinity, so at point C, one force is exerted by Q1 and another one force is exerted by Q2. So two work has to be done by Q3. So first one due to Q1, that is W3 equals to 1 by 4 pi epsilon naught Q1 Q3 by R13, and due to Q2, W4 equals to 1 by 4 pi epsilon naught Q2 Q3 by R23. R23, R12, R13 is the distance from the charges each other. Okay, so total work done. Now this 3 is consist a system. This behaves as a system of 3-point charges. So the total work done is W1 plus W2 plus W3 plus W4. W1 is 0. So we have only 3. Put the values here. So we have 1 by 4 pi epsilon naught Q1 Q2 by R12, Q1 Q3 by R13 plus Q2 Q3 by R23. And we know that the total work done is stored as a potential energy inside the system. So U equals to this one. So this work done is stored as a potential energy. So U equals to 1 by 4 pi epsilon naught this one. Understand? This is for three body charges. Clear? Now, next topic is electric units of electrostatic potential energy. Okay, normally for measure the potential energy we use the joule, but one branch of a physics that is called atomic physics. In your syllabus also with their atoms and nuclei, but very few topic is there. So in atomic physics, where we studied about the atomic structure, hydrogen spectroscopy, many things is there, radius, atoms radius. Okay, so that is very small things. Atoms, we know that atoms means very tiny particle of the matter. So in atomic physics, when we calculate the energy in that branch of physics, we use another one unit of potential energy that is called electron volt. It is denoted by EV, small e, capital V. And when this EV is converted to joule, so 1 EV equals to 1.6 into 10 to the power minus 19 joule. This is a charge of an electron. Okay, so how we define the electron volt? The electron volt is a potential energy gain or lost by an electron in moving through a potential difference of 1 volt. So if the potential difference is 1 volt, in that potential difference, if the electron is moving from one point to another point, that is called electron volt. And we know that one electron volt means one electronic charge into 1 volt, and electronic charge is 1.6 into the minus 19 into 1 volt. Okay, that is called joule. Now here a few another units also we use for calculating the potential energy. 1 MeV, milli electron volt, that is equals to 10 to the minus 3 eV. So that is equals, when we convert it into joule, 1.6 into 10 to the minus 22 joule. keV, kilo electron volt, that is equals to 10 to the power 3 eV, 1.6 into 10 to the minus 16 joule. And MeV, million electron volt or mega electron volt, 10 to the power 6 eV, 1.6 into 10 to the minus 13 joule. 10 to the minus 13 minus 16 minus 22, it's a very, very, very small. That's why we use the EV. And if you studied in a higher study, if you choose this topic, atomic physics, you know many things related to electron volt. Okay. Next, potential energy of a dipole in an uniform electric field. So we in the last this topic here we studied the potential energy due to a 3-point charges, 2-point charges. Now due to a dipole. Dipole means two equal but opposite charges separated by a distance is called dipole. Di means two pole is there, that's why dipole. That dipole is placed in an uniform electric field. So this is a diagram as shown in the figure. So when it placed at the 2-point charges, that means plus q and minus q, one force is exerted on it, and that is due to plus q, that is plus qe towards this side, and this side is minus qe. So total force F equals to plus qe minus qe equals to 0. We also prove in the first chapter. So this force forms a couple, and that couple is called torque. Okay, so torque exerted by the couple will be tau equals to what? Tau equals to the perpendicular distance between the charges into any one charge, any one force into perpendicular distance between the charges. So force, any one force, that is the magnitude. Minus and plus is due to the minus q and plus q, but the magnitude is qe. So qe into 2a sin theta, that is the perpendicular distance between them. And we know that from the definition of electric dipole moment. Dipole moment means q into 2a, charge into distance between them, that is called P. So in place of 2a into q, we can write Pe sin theta. So tau equals to Pe sin theta. Now, if we rotate this electric dipole through a small angle d theta, this is angle theta, small angle d theta. So one small work has to be done by this electric dipole, and this dipole W equals to, we know that from the definition of work done, force into displacement. So dW equals to tau. Here force means this tau into d theta, the angle change. Displacement means here angle change, d theta. So we know that the expression of tau, so Pe sin theta into d theta. Now the total work done, like this way, if you change, first this is theta, then d theta, then again d theta, then again d theta. Okay, so total work done in rotating the dipole from, suppose, starting from theta 1 to theta 2, between two angles theta 1 to theta 2. So what we can do? Integration. W equals to integration of dW, integration theta 1 to theta 2, Pe sin theta d theta. So after integration, we have Pe cos theta 1 minus cos theta 2. Now we know that the work done is stored as a potential energy. So potential energy, this one is a potential energy, U equals to Pe cos theta 1 minus cos theta 2. Now if the dipole rotates theta 1, that first of all we consider theta 1 equals to 90 degree. Okay, then that is perpendicular direction. Theta 90 degree means the angle between electric field and the dipole is 90 degree, and theta 2 equals to theta. So if we placed here, so we have U equals to minus Pe cos theta. Cos 90 value is 0, minus cos theta minus Pe cos theta, and cos theta means what? Dot product. So that is equals to minus P dot E. So potential energy is a scalar quantity. From this expression we can understand potential energy is a scalar quantity, not the vector quantity. When dot product between two vector is called the scalar quantity, it gives us a scalar quantity, minus Pe cos theta or minus P dot E. Now it has some special cases. What is that special cases? Depending upon the value of theta. So one is a stable equilibrium, unstable equilibrium. That means when potential energy is maximum, when the potential energy is minimum, when the potential energy is 0. This is a 3 special cases. Okay, we also studied this type of stable unstable in the first chapter when we studied the dipole placed in a uniform electric field. When we first understand, or we first studied the concept about torque. Okay, let it be. Okay, first is the position of a stable equilibrium. Stable equilibrium when when the dipole and the electric field is stable, and the answer is when theta equals to 0 degree. Theta equals to 0 degree means when the dipole moment's direction negative to positive. Okay, or you can say that when the dipole and the electric field are parallel to each other, the angle between them is 0 degree, because when they are parallel to each other, the less amount of force acts on the charges. So if the very less amount of force, or we can say no force, acts on the charges, so it can create any couple or any torque is there. So this is a stable position, no disturbance is there. So when it is possible, when theta equals to 0 degree. So in this equation, if you place theta equals to 0 degree, you have U equals to minus Pe. So minus Pe, that is a minimum potential value of the potential energy. So this is a stable equilibrium position when theta equals to 0 degree. That means dipole moment and electric field, you can say that, or you can say that dipole and the electric field are parallel to each other. So in this case, potential energy is minimum. Now position of an unstable equilibrium. When it is unstable, when they are anti-parallel to each other. Okay, electric field is this side, but the dipole is this side. So this is a anti-parallel direction. So maximum force is exerted on it. So that means theta equals to 180 degree. Okay, and in that case we get the maximum potential energy. U equals to minus PE cos 180 degree, cos 180 value minus 1, so minus minus plus, that is equals to P into E, maximum potential energy. This is the minimum potential energy, but in a stable equilibrium this is a maximum potential energy. That means maximum force is acts on the charges. So torque also be maximum when theta equals to 180 degree. Okay, and zero energy when it will be zero, when they are perpendicular to each other, when the dipole moment perpendicular to the field. So theta equals to 90 degree, theta equals to cos 90 value is 0, so potential energy is 0. This is the three special cases. You remember this. These three is a very important. Many times it will come for in a board exam. This proof for potential energy, proof this one, and the special cases. Discuss the special cases for stable and unstable. This one also not come, but this two, stable equilibrium, unstable equilibrium. When we get the minimum potential, when we get the maximum cases, students have. Students write here potential energy maximum, potential energy minimum. So number is deducted. Please remember this one. Stable equilibrium, less minimum potential energy. Unstable equilibrium, maximum potential energy. Clear? Okay. Now let's do some numericals. Okay. First numerical, 3 charges is there. Minus q, plus q, minus q are placed equal distances on a straight line. If the potential energy of the system of 3 charges is 0, find the ratio of q by q. Okay. So as shown in the figure, we consider A, B and C. At point A minus q, at point B plus q, at point C minus q, and equal distances are there. So A to B are, B to C are. So, and it is given that potential energy of the system 3 charges is 0. So potential energy of these 3 charges, what is the potential energy? We know that 1 by 4 pi epsilon naught q1 q2 by r. So due to these 3 charges, 1 by 4 pi epsilon naught take common, minus between these two, minus q plus q by r. Okay, between these two, minus q by 2r, and between these two, plus q minus q by r. Now after solving, we have the ratio q by capital Q by small q, that is equals to 1:4. Clear? Okay. Now next one. An electric dipole of length 2 cm is placed with its axis making an angle of 60 degree to a uniform electric field of 10 to the power 5 Newton per coulomb. If it experiences a torque of 8√3 Newton meter, calculate the magnitude of the charge in the dipole and potential energy. It's very easy. So what is given? Length 2a is given, 2 cm means meter, converted to meter. Theta angle is given 60 degree, E is given, tau is given. So magnitude of the charge on the dipole. So we use the expression of torque, because in their torque P is there and P is a dipole moment. So in place of dipole moment, we can write Q into 2a. So from that expression we can find out the Q. So tau equals to P sin theta. P means 2a into Q, E sin theta. Now if we put the values, Q is unknown, so Q equals to 8 into 10 to the power minus 3 coulomb. Now potential energy of the dipole. What is the potential energy? U equals to minus PE cos theta. And in place of P, we write Q into 2a minus. So minus Q into 2a into E cos theta. Put the values Q 2a E cos theta. We have U equals to minus 8 joule. Next, find the amount of work done in arranging the 3-point charges on the vertices of an equilateral triangle ABC of side 10 cm as shown in the adjacent figure. This is also come in CBSE sample paper. Okay, this type of numericals also come in exam. As shown in the figure, ABC one is a triangle. At point A, 6 microcoulomb is there. Microcoulomb means 10 to the power minus 12. 10 to the power minus 6 coulomb. At point B, plus 6 microcoulomb. At point C, minus 6 microcoulomb. So work done due to this total work done. So first of all, we have 3. First, in between these two, AB, in between these two, in between these two. So 1 by 4 pi epsilon naught take common, Q1 Q2 by AB, Q1 Q3 by AC, Q2 Q3 by BC. Now put the values and solve this one. We have minus 3.24 joule. Understand? Like this way we can solve the numericals. It's a very easy numericals. Directly we use because work done is very easy. First between these two plus this two plus this two. This is the system. 3 charges is there. Okay. This type of numericals will come in the board exam, and this related to potential energy numericals are very easy. If you remember this formula, this is for potential energy due to a dipole, and this formula due to the 3 charges. This is the potential energy due to the 2 charges. If you remember this one, then you can easily solve any type of numerical. Okay, understand? If you have any doubt anywhere, please write in your comment box. Write in the comment box. Okay, thank you. Bye bye.